All right, so look, I'm a novice, right? But as you said, it got close to the sun. It changed colors because it got hotter. Wouldn't that be natural, though, as it was more impacted by the sun's gravitational pull and it got closer to the sun? So you're saying that this is something more than that, which would naturally happen.
It did get hotter, but it's still much cooler than the surface of the sun, which is 5,800 degrees. And so we would expect it to be redder than the sun.
As Comet 3 I Atlas moves closer to the inner solar system, astronomers are noticing two changes that tend to grab attention fast. It is getting greener, and it is getting brighter. To casual observers, that combination sounds dramatic, even ominous, as if something unusual or unnatural is happening. In reality, what we are seeing is a textbook response to sunlight, amplified by the fact that this object did not originate here. The changes are real, measurable, and fascinating, but they are also entirely explainable once you understand what activates comets and how light interacts with the material they release. Brightness is the easier part to explain. Any object approaching the sun receives more light. More light means more reflection. Even a dark, dusty surface will appear brighter as the distance decreases. But comets are not simple reflective rocks. They are volatile, rich bodies, and when they warm up, they begin to release gas and dust. That released material spreads out around the nucleus, forming a coma that can be thousands of kilometers wide. The coma dramatically increases the surface area interacting with sunlight. Instead of reflecting light from a single solid object, the comet is now reflecting and emitting light from an expanding cloud. That alone can cause brightness to increase faster than distance alone would predict. In the case of 3I Atlas, this effect may be especially noticeable because early observations suggested it was relatively inactive. That created expectations of a steady, predictable brightening curve. When activity begins, even at a low level, it can look sudden by comparison. The comet did not suddenly change its nature. It crossed a thermal threshold where certain compounds could finally sublimate, and the visible result is an increase in brightness. The green color is a more specific clue. Green comets are not rare, but they are often misunderstood. The color does not come from green ice or green dust. It comes from gas. When carbon-bearing molecules are released from the comet's surface, ultraviolet radiation from the sun breaks them apart. Some of the fragments temporarily form molecules like diatomic carbon, known as C2. These molecules fluoresce, emitting light at a wavelength that appears green to our instruments. This process does not require a large amount of material. Even a thin cloud of gas can produce a detectable green glow if the conditions are right. Sensitive telescopes can isolate these emissions using filters or spectroscopy, confirming that the color change is real and not an artifact of imaging or processing. When astronomers say 3I Atlas is getting greener, they mean that the relative strength of these emission lines is increasing compared to reflected sunlight. The timing of this change offers important clues. Different compounds activate at different temperatures. Water ice requires relatively strong heating, while substances like carbon monoxide and carbon dioxide can sublimate much farther from the sun. If 3I Atlas is showing green emission earlier than a typical solar system comet would, it suggests that its surface or subsurface contains highly volatile material. That makes sense for an interstellar object, which may have formed in a colder or chemically different environment. Another factor contributing to both brightness and color is speed. Interstellar comets move faster through the solar system than most native comets. That higher velocity increases interaction with the solar wind, the constant stream of charged particles flowing outward from the sun. When neutral gas released by the comet interacts with this wind, it can become excited and emit light more efficiently. While this effect is subtle in visible wavelengths, it can enhance overall activity and make changes appear more pronounced. It is also important to understand that approaching Earth does not mean danger or proximity in any dramatic sense. Astronomical distances remain vast. The changes being observed are driven primarily by the comet's distance from the sun, not its distance from our planet. Earth just happens to be in a good position to observe the process clearly as it unfolds. As the comet brightens, observers may notice that its brightness does not increase smoothly. Instead, it can fluctuate. These variations are often caused by rotation. As 3I Atlas spins, different regions of its surface are exposed to sunlight. If some areas contain more volatile material than others, activity will vary over time. This can create periodic brightening and fading, revealing information about the comet's shape and surface composition. Dust plays a supporting role here as well. Gas escaping from the comet can drag dust grains with it. These grains scatter sunlight very efficiently, especially at certain angles. Even a small increase in dust production can significantly boost brightness without changing the comet's intrinsic size. Dust does not contribute to the green color directly, but it makes the entire coma more visible, allowing gas emissions to stand out. The fact that 3I Atlas is interstellar adds another layer of interest. This is not just another comet doing what comets do. It is a sample of another planetary system responding to our Sun for the first and only time we will ever see. Its brightening and greening are not just visual effects. They are data points. They tell us which molecules survived interstellar space, how radiation altered the surface, and how quickly activation occurs when a foreign object encounters a new star. Importantly, nothing about this behavior suggests anything artificial or anomalous. Green emission is one of the most well-documented signatures of cometary activity. If anything, its presence strengthens the case that 3I Atlas is a natural object governed by the same physical laws as everything else in the solar system. Technology tends to produce sharp, controlled signals. Nature produces diffuse glows, mixed chemistry, and gradual transitions. As 3I Atlas continues inward, the balance of gases may change. Green emission may intensify, then fade, as different molecules take over. Other colors, such as faint blue from ionized gases, could become detectable under the right conditions. Each phase adds depth to the story and helps refine models of interstellar debris. What makes this moment compelling is not mystery for mystery's sake, but familiarity in an unfamiliar context. A comet from another star is behaving like a comet when warmed by sunlight. That tells us something powerful about the universality of physical processes. Carbon chemistry behaves the same way here as it does elsewhere. Ultraviolet light excites molecules the same way around every star. So yes, Comet 3I Atlas is getting greener and brighter as it approaches Earth. Not because something unusual is happening to it, but because something ordinary is finally becoming visible. A cold traveler is warming up. Gas is escaping. Molecules are glowing. And for a brief window of time, we get to watch a visitor from another solar system respond to our Sun in a way that feels both familiar and extraordinary at the same time.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.